Welcome to NeuroForge, a microscope for neural networks. This is the first in a three-part series. In just a few minutes, you'll see exactly how a neural network learns. We'll start with the simplest possible network. Think of it like a Lego brick, easy to snap together, but powerful when combined. Then we'll tackle the infamous exclusive OR problem. This tiny data set triggered the AI winter of the 1980s. We will end with the Titanic. Does a layer of 24 neurons work better, or will 8 do the trick? You're going to love the answer. So let's dive into a quick walkthrough and you'll be running in no time. Now, traditionally arrows represent weights, but weights don't flow anywhere. Think of neurons like functions. Inputs come in, the neuron transforms them, and then passes along its output. So in NeuroForge, weights are inside the neuron, and arrows show the output from one neuron to the next. Now, if multivariable calculus is your jam, you can approach it that way, but I see it more as a brute force operation. At its heart, it's just three simple steps repeated over and over. Step 1, predict. Look at the input and make a guess. The bear sees solid build and predicts 250 pounds. In our network, this might be credit score is stellar, predict the loan will be repaid. Step 2, check. Compare the guess to the actual result. The scale says 240. Papa Bear was over by 10 pounds, and Mama Bear is not happy about it. In our network, the training data is loans that have finished, so we know both the input and the result. Step 3, nudge. Adjust the weight so you're closer next time. He's not going to make that same mistake twice, and to be honest, it wouldn't hurt to compliment the dress as well. That's it. Now repeat until it either learns or gets stuck, and sometimes it does get stuck. That's where NeuroForge comes in. It starts over here with the training data. You can see we have 8 samples of training data that we will run up to 30 times. Each sample is a credit score from 1 to 100, representing the chance of repayment. By the way, if you hover over a sample, you'll see the exact file used to generate it, hopefully with decent doc strings. Back to our 3 simple steps. Our first sample has a score of 96, the input, and they paid it, so the target is 1. The prediction is input times weight plus bias, so that is 116. And we can confirm it by hovering over that neuron, and the left side is the prediction, also known as forward pass. Step 2, check it. To check, we do 2 things. Calculate the error, which is how far off the prediction is. That's simply target minus prediction. So we have negative 115 error. Second, classify it. Does that mean we predict payment or default? Well, if it's greater than 0.5, we classified it as paid. So in this case, we got it right. But the error is really high. And that's where the last step comes in. Nudge it. We take that large error and run it through a loss function. To keep it simple, we used MSE. MSE takes that error of negative 115 and gives us a gradient of 230. I like to think of gradient as blame. So we take that blame, multiply it by the input and a learning rate. The learning rate turns it from a big push to just a nudge. You can see those calculations on the right-hand side. Notice the last 2 columns. Before shows the current values. Note how they match the weight column from the forward pass. After is what it will be next. In this case, negative 0.002 and 0.989. And if we move one sample, sure enough, that's what it is. And that's the whole thing. But look at the third sample. It gets classified wrong, and that's why we repeat. So we run it again and again and again. The weights stabilize, and the average error comes down. You can also see it on this graph. Now, if you're anything like my wife Sonia, you'll say accuracy of 87.5. What about the other 12.5%? To meet her standard, we'll need to add a bit to our model, but still just 3 steps. Let's look at both versions side by side. First, notice how the graph clearly shows the difference in results. The first one started with an average error of 50 and never got it perfect. The new one started with an average error of 0.3 and got perfect classification in just 10 epochs. How? Well, we switched to the textbook loss function for classification known as BCE, binary cross entropy. And with BCE, the output neuron needs a sigmoid activation. But wait, how do I know if these models are actually comparable? Just hover here for the architecture comparison. It shows every difference. No activation versus sigmoid, MSE versus BCE. But wait, it shows a learning rate change too. MSE had 0.0001 and BCE is just 0.1. Why? Well, anytime you change anything in the config, it throws the learning rate off. And it's so easy to get the learning rate wrong. Boo. We like things that are impossible to get wrong. So unless we're actually studying learning rate and doing experiments, we always use an automated learning rate sweep. It does a quick test from 1 to 0.000, 14 zeros and then a 1. And it uses the best learning rate it finds. This way, you never need to set a learning rate again. And even better yet, you never have to worry about getting them wrong. Here's what the learning rate sweep looks like. Notice how it gets real low and then starts to rise again? So, does using the textbook loss function find that 12.5% Sonia was looking for? Well, you may have noticed another difference too. The BCE model scales the inputs. Let's add a scalar to MSE so we're comparing apples to apples. So MSE can solve it too, but BCE did find it faster. Do you think I'm bullshitting you? Good. Open source drop soon. Sign up for early access now and go prove me wrong. Happens all the time. I'll wait. That's Perceptron. Simple but powerful once you see it. Next up, exclusive OR. Again, this tanked AI in the 1980s, but I'll show you an optimizer that leaves gradient descent in the dust. And to wrap the series up, we're going to look at the Titanic. We'll have information like ticket price, where did they embark from, family size, and predict who survives. Get early access to the open source, link below. Thanks for watching. Peace.